this would happen.
It was horrible.
It was horrible.
What was even happening?
Yeah, how did your AP look?
Okay, so I want to talk about, it was actually on that assignment that I just gave back. And this is where this gets a little bit wonky mathematically in terms of sign. And it's this question number 5, it's question number 5, because this is relative to today's as well. So if you look on number 5, you've got some random nucleus, okay, or group of positive charges. And you have an electron that's moving from this point on a trajectory out to here. So there's your initial point, and there's the final point, okay? So let's just start with, leave out OOI out of the whole mix. Leave OOI out of the mix for now, okay? We'll deal with OOI later. Let's just start with kinetic energy. Because kinetic energy is 1/2 mv squared, can kinetic energy itself ever be a negative number?
No.
No. Okay, kinetic energy can never be a negative number. So, with that said, since this is a negatively charged particle, and it's moving further away from that positive charge,
Oh my gosh, I'm
as it moves further away from the positive charge, what's it going to do?
increased. Oh, I'm sorry, I'm still thinking about OOI, sorry.
What's going to happen to the velocity of the electron as it moves away? It's going to do what?
It's gonna go down.
It's going to slow down, right? Everybody cool with that idea? It's like stretching a spring,
It's
right?
weird gravity.
So you're increasing that distance. It's going further away, right? So right away, you know the value of your kinetic energy is going to become less, right? Good with that, because the fact it's getting further away. Now, you know that your OOI plus your kinetic energy has to add up to a constant, right? Because energy has to be conserved. So, as this thing is getting further away, the value of the kinetic energy is becoming smaller. So, now, your OOI, Andrew had the point about OOI, so if you look at OOI, which is K, Q1, Q2 over R. Because of the fact that these have opposite charges, what's going to be the sign of OOI? OOI is going to have a negative sign, right? So I'm going to have some negative number plus my kinetic energy equals a constant. So let's say you want that constant to be 20. Pick a number, doesn't make any difference. Let's just make it easy and say it's 20. So, as that kinetic energy is going away, the kinetic energy value, which is positive, is becoming a smaller number, right? Because of the fact that it's moving away from it and the fact that it is slowing down. So then, what's going to happen then to OOI to always produce the same value of 20? Because it's a negative value, what has to happen to it? So let's make up a number. Let's say that's 18, and then it drops to 16, just to make up a number. So if this is 18 and everything has to add up to 20, then, no, I screwed that up. Let's make that 22. Make it 24 and then 22. So if this is 24, then my OOI has to be -4. That's going to add up to 20. So then if this drops to 22, then that has to become -2. And so when you look at this, is one of the very few instances that negative sign kind of works like mathematics does. Because if you were in a mathematics classroom and I asked you to compare -2 to -4, y'all are math nerds, which would be the bigger number, -2 or -4? -2, because it's closer to 0. So the whole idea here is that energy has to be conserved. okay? So when you look at number 5, and number 5 was without doubt the most question on that assignment that I just gave back, okay? Start with the idea of what's going to happen to the kinetic energy, okay? As that electron goes away, because of the fact that it's being attracted to it, so as that electron goes away, it's going to slow down. That's going to decrease the kinetic energy, and then you're off to the races. Okay, so let's talk about the assignment from yesterday. So there's some specific ones that I want to go over. On the questions side of this, and I heard some debate going on about number 7 even yesterday. So you've got positively charged, and then you've got some negative charges up here, and then you've got some positive charges down here. Okay? So start with this idea. What you're going to do is that 2 protons are launched with the same speed from point 1, one path moves to the other. Is U1 the change in potential energy along the path larger, smaller than, or greater than? Explain. Okay? So this thing is going to move through a voltage because of the fact that it's going to, and the only difference is the path that it's going to take. So if you look at delta U equaling Q delta V, okay, is the distance that it travels going to be a factor in that calculation? No. It's just like I have this tennis ball. I can either move the tennis ball up a ramp and increase the gravitational potential energy, or I can lift it straight up. In both situations, whether I roll it up a ramp or if I lift it straight up, in both situations, is the change in gravitational potential energy going to be the same? Yes, because the path length doesn't make any difference. Keep that in mind when you answer number 7. Okay? Look at what is a factor and what is not a factor. Now, when you get to question 13, okay? Here's the only thing I want to see on 13, and the same thing is true on number 11. I want to see greater than, less than, or equal to. I don't do commas, okay? So that's what I want to see. Greater than, less than, equal to, okay? Commas don't work for me. Yes?
Is it based off the magnitude or like charges?
Magnitude.
Okay.
Okay, so let me give you a hint. Like on number 11, you should have a whole bunch of equal signs on number 11. Okay? You should have a whole bunch of equal signs on number 11. On 13, all but one of them should have an equal sign. Okay, so on number 13, all but one of them should have an equal sign. There's only one of them that does not. Now, let's talk about question 19, and this is about verbiage. So, on number 19, and this is question number 19. So you got a parallel plate capacitor. Simple way to model this is take 2 pieces of styrofoam and charge them up. That's an easy way to do this. So you're going to hook this thing up to a battery, and that's what I tried to show you yesterday. Okay? Hook it up to a battery. That's going to create, that battery is going to do the work to create a charge and an electric field within that capacitor. Okay? Capacitors aren't going to charge themselves. If they did, you wouldn't have to plug your phone in at night. Okay? You have to have some source of energy to do this. So what's important about the verbiage on number 19? Okay? It says connected to a battery has a potential difference of delta V. It could be 12 volts, 7 volts, whatever it is. So without breaking any of the connections, insulating handles are used to increase the plate separation to 2D. So the important part of that statement is that you're going to pull these things apart. You're going to use insulating handles. So you're not going to give any place for those electrons to travel because of the fact that you're going to have insulating handles. Now, So on 19A, does the potential difference change as the separation increases? If so, by what factor? If not, here's what you got. So the beauty of what's happening on 19 is that it's still connected to the battery, okay? Since it's still connected to the battery and that battery is still generating that potential difference, what's going to happen to the voltage? Increase, decrease, stay the same. Will Stanley.
The same.
Yeah, it's going to stay the same because it's hooked up to a battery. So 19A, the voltages are going to stay the same because it's still connected. That's going to be important later on. So my voltages are going to stay the same. Then when you get to B, it says, okay, does the capacitance change? By the capacitance, I'm talking about the value of uppercase C, that big C. And it says, and so by what factor? So if you look at capacitance equaling epsilon naught A over D. So in this situation, you're not going to change epsilon naught because that's a constant. It's tough to change that number. Your area isn't going to change because it's still the same plates. But you are going to double the distance. Because you're going to double the distance, then what's going to happen to your capacitance? It's going to be half as much. Okay? So, now, here's the next thing. Does capacitor charge Q increase, decrease, or stay the same? So, the other way that you can look at capacitance is that it's charge over voltage, okay, Q over V. So this is where this plays out. So this is where you kind of have to combine your answers to 19A and 19B to get your answer to 19C. So on 19A, we said the voltage stayed the same because it was still hooked up to the battery. So my voltage is staying the same. It's not going to change. We just said on 19B, the capacitance is going to become half as much. So if the voltage stays the same and my capacitance drops to a half, what has to happen to my value of charge? It has to be half as much. Okay? Cool with that idea. Because of the fact that it's still hooked up to the battery. Now, what was the other one with capacitors in the battery?
I think it's 10.
Yes. So here's the difference with number 10. So you got it separated by a distance charged to a potential difference. All the wires and batteries are disconnected. So what's happening on number 10 is that we charge this thing and then we disconnect it from the battery. Okay? So it's no longer connected to the battery. So again, we got to talk about 10A because if 10A is wrong and you're off on the wrong foot, then everything else is going to change. So on 10A, it asks for the charge. Okay? So if you look at that in terms of capacitance, it's not A over D. So on this one, does capacitor charge as the separation increases, if so by what factor? So on this one, because of the fact that it's been separated and it's no longer hooked up to the battery, your charge is going to stay the same because there's no inflow or outflow of charge. That's a fixed value at that point because that becomes an isolated system. So your answer to 10A is the charge is going to remain the same. Then, after that, then you're off to the races. Because then you realize, oh, okay, the charge is going to stay the same. Now, on B, it asks for what's going to happen to, I think B is the electric field.
Yes.
Okay? So if you look at how you calculate electric field, which is E equals Q epsilon naught over A. Well, if your charge is staying the same, and that's why you have to get this started right on number 10, if your charge is staying the same, and your area is staying the same, the value of your electric field has to stay the same. Okay? So that's why, that's kind of that difference between 10 and 19. So on the problems, On 6 and 7, so 6 and 7 are kind of cool because of just the concepts. So the only difference on 6 and 7 is that one is an electron and one is a proton. Okay, that's the only difference between the two of them. So on 6a it says, what is the kinetic energy in electron volts? So here's the story. So you got delta U equals Q delta V. This is where you look at the units. So because of the fact that it's electron, you've got 1.6 times 10 to the negative 19th coulombs. What are the units for volts? Joules per coulomb. So you've got 1,000 volts. So that's 1,000 joules per coulomb. Coulombs cancel out, you get joules. Okay? So out of this calculation, you get units of joules. It's not what the answer is asking for. The question asks for this value in electron volts. Okay? Now, on the purple sheet, you have a handy-dandy conversion of electron volts to joules. 1.6 times 10 to the negative 19th joules is equal to 1 electron volt. And the reason that that has the same value as charge is because that's the charge on an electron or proton. That's why it's called an electron volt. Okay? So basically, you're going to multiply by 1,000, and you're going to get 1.6 times 10 to the negative 16th joules. Then you're going to go, 1.6 times 10 to the negative 19th joules is equivalent to 1 electron volt. So your answer to 6a, oddly enough, is just going to be 1,000. Okay? Basically, you multiply by 1.6 times 10 to the negative 19th, and then you divide back by 1.6 times 10 to the negative 19th. Okay? Or you can just look and go, okay, right, it's an electron. It's accelerating through 1,000 volts. That would be 1,000 electron volts. So if you wanted to think of it that way and go, okay, right, it's just one electron and it's being accelerated through that, it's 1,000 electron volts. I don't care how you think about it, it doesn't make me any difference. Now here's the difference when you get to C. So on C and on 6 and 7, the difference is the mass. On 6 you have an electron, on 7 you have a proton. But they both have the same energy because they both have the same charge and they're both accelerated across the same voltage. So 6a and 6b is the same as 7a and 7b because it's still the same charge and it's still accelerated across the same voltage difference. Okay? The difference is the velocity. So if you're going to have the same energy, and kinetic energy equals 1/2 mv squared, so if the kinetic energy is the same, as the mass gets bigger, your velocity has to be less. So the velocity on number 6 is 10 to the 7th. Your velocity on number 7 is 10 to the 5th. Okay? On number 8, so question 8, so you got a helium ion from rest to a speed of 1.0 times 10 to the 6 meters per second. What potential difference is needed? So here's what you've got to do on kind of the sequence on number 8. The first thing that you've got to figure out, oddly enough, is the kinetic energy, which is 1/2 mv squared. The tricky part here is that you have to have the mass. Well, and this is the little note that I said, oh, hey, a helium nucleus is 2 protons and 2 neutrons. So, yes, it technically has 3 electrons. Relatively speaking, the electron mass doesn't matter because electrons are about 1,800 times lighter than the mass of a proton or neutron. So technically there's 3 electrons, but that's like driving your car and you run into a mosquito, okay? It's not going to make any difference. What, Cohen?
I just thought of something you said a little bit earlier, how you said there was a difference between the mass of a proton and a neutron.
But it's only when you get into very, very strict calculations involving Einstein's theory of relativity.
Yeah, but how? Wouldn't that mean energy would have to have mass?
That's why it's E equals MC
Remember
squared.
me asking the question
Oh, I
yesterday
guess
about
it
what
makes Okay.
And as you get older, you have less energy and more mass.
Oh. That's why you move slow.
I know, yeah.
That'll make
Time,
sense now.
but time goes faster, it's kind of weird. Okay, anyway, so on number 8, the first thing you have to have is that kinetic energy. Now, that change in the kinetic energy, oddly enough, is also gonna equal the change in your potential energy. In this case, the change in OOE, which is also gonna equal the work that's done. So once you get that number, which should be 10 to the negative 15th, if I remember right. So that K is gonna be 10 to the negative 15. Okay, you gotta have that number. Then from there, you can go, oh, delta V, or U, equals delta V times Q. So that's going to be your value there. You know the charge because of the fact that this has only lost one electron. So your charge is going to be 1.6 times 10 to the negative 19th. And then solve for your voltage. So on number 8, if all goes well, it's going to be a not so good GPA times 10 to the 4th. Cool with that. Now, speaking of contrasting, let's talk about questions or problems 9 and 10. Okay? So, here's an electron, right? And it wants to know, it's brought to a rest, does the electron move into a region of higher potential or lower potential? So, let's just forget the fact that it's plates, let's just look at a broad idea. And the same thing is going to happen on number 10. So, forget electric fields, just look at this. So let's say that here's something that has a positive charge. Okay, couple of protons, I don't care. Couple of very optimistic people that have positive, I don't care. Something has a positive charge there. So, are the voltages around that positive or negative? Positive. So this might be positive 100 volts, this might be positive 50 volts, because the farther away you get, the voltage becomes smaller. True? And then out here, you're down to like 20 volts, whatever. Okay? So, if I let an electron go in this direction, I let the electron go in that direction, from low voltage to high voltage. If it's an electron, listen to me very carefully, there's a huge caveat to this. If it's a negatively charged particle moving towards a positive source that's generating the field, what's the electron going to do?
Slow down.
Speed up or slow down?
Slow down. Towards the negative.
The electron is moving towards a positive charge.
Speed up. Speed up.
It's going to speed up.
Like a shift reaction.
So if it goes from low voltage to high voltage, what's it going to do? It's going to speed up. What do you want it to do?
Slow down.
You want it to slow down.
So you gotta do something.
You got to do something.
You gotta do something.
How about we shoot it in the opposite direction?
Yeah, okay. That works.
If that happens, what's it going to do?
Slow down. Slow down.
Slow down. So, what's your answer to 9A? Low to high or high to low? High to low, because you want it to slow down. Okay? So I'm going to go from high voltage to low voltage. Now, in contrast to that, you have question 10. A proton with an initial speed of 800,000 meters per second is brought to rest by an electric field. If I shoot a proton towards there, what's it gonna do?
Slow down.
That's gonna slow down. So if you want a proton to slow down, you want it to go from low to high. Okay? Does that make sense?
Yes.
Okay? Cool with that thought process. Now, on number 9, your answers are going to be pretty small numbers. Okay? Less than 1 on B and C. Okay? On number 10, you're going to have really big numbers. Okay? Over 3,000. Okay? So, your answers to B and C on 9 are the same. One might be negative, I'm just saying. And then on 10, both of those answers on B and C are going to be the same. Both of those might be positive. I'm just saying. What?
That's a big
Thought they said one might be negative. Wait, 10?
On number 14,
No, I thought they were
your answer to B on that value of that electric field should be something times 10 to the 5th. 14B.
Okay. I thought you just moved on to 12. I think kind of. No, I don't even know. That's what I'm being.
Your answer to 14C should be something very, very, very small. Like 10 to the negative 17th small.
It's not that small.
What do you say for B?
At best. Maybe. Your answer to number 28, let me give you a hint on 28. You've got to use capacitance equals Q over V. In microcoulombs, which is something that you hate with all your heart and soul. So on that one, that you're in microcoulombs, it would make a non-weighted phenomenal GPA. Well, you like that answer?
I do like that answer.
Your answer to 30 should start with a 3.
Is it possible to get the GPA in 28 as the charge is negative?
Oh, absolutely.
The difference.
Yeah. You'd have
I
to
think it's
have,
kind of hard to get a GPA.
no, yeah.
Well, it depends on your scale.
No, it's a non-weighted GPA.
Depends on the scale.
Yeah.
I had options up to a scale of 100 for some reason.
Would that make this negative? Would that make the
Okay. Any other questions?
because it just condenses?
Going once? Twice?
Say something.
Question or problem?
Problem.
Can you go back?
Oh, is that where it's one worth like at 25%?
Yes.
That's a good one.
Is that it? It's just because no sense because it's still hooked up with
Now, I hate fractions, so I'm gonna show you what I did. There's other ways that you can do this, Preston. I'm just gonna show you how I approach it. Okay? So, halfway in between, you're at 300 volts, right? Okay? And you know that voltage equals KQ over R, right? True? So this is what I did. I let this entire distance here
Using full value.
be 2R. Okay? Cool with that. You could let it be R, you could let it be X, you could let it be 4R. I just let it be 2R. Now, if that's 2r, then what's this distance going to be? It's kind of a pirate thing. This is the pirate approach to the problem. R, I got 2 R's. Okay, right? Cool with this. Now, would you agree then to get that 300 volts if I take KQ over R and add it to KQ over R, I would get 300 volts. You agree with this? Okay? If I take KQ over R plus KQ over R, what do you get? Just don't worry about the 300. If I take KQ over R plus KQ over R, what do I get?
2KQ over R.
2KQ over R equals 300. True? So, would you agree then that KQ over R equals 150? Would you agree to that? Now, this is going to be important, okay? This is going to be important. There's an equal sign in there. So if I have 150, that's equivalent to KQ over R, or if I have KQ over R, that's equivalent to 150. Good with that? It's subtle, but there's an equal sign there. Okay? Now, if you don't like this, you said, oh, I just want this to be R. Cool. Well, that's going to be R over 2 and R over 2, and this is going to be R over 2. It's just going to muddy the waters. Okay? It's the same process, but it would just, and you all know how I feel about fractions. Okay?
You
Just
love
say
them.
no. That's why let the total distance be 2R. Okay? Now, this is where it gets a little bit tricky, because now I do have to deal with fractions. So now, I'm at, what is it, like 25%? So, since I let this be here, and this is going, let me, so that we're not dealing with that. Okay. I hate the eraser on this thing. All right. So this is R and this is R. So it doesn't make any difference. I'm going to pick this side over here, and I'm going to have this point right there. So this side over here, would you agree would be R over 2? So then what's this distance over here? Yeah, 1.5 R or 3R over 2. Okay? Does that make sense? So this distance over here is going to be 3R over 2. True? Now, here's what you want to look at. So your voltage is going to equal the sum of these two values, which is going to be KQ, and then this is going to be R over 2, right? Good? And this is going to be KQ and then 3R over 2. Okay? Now, can you add those values together and get it in terms of KQ? Sure you can. Okay? It gets ugly with the fractions. Okay? But think about this. This is 2. Would you agree that that's 2 KQ over R? Would you agree to that? Would you agree that that's 2 KQ over 3R? So what's the least common multiple of R and 3R?
3.
So what would you have to do to that?
3 over 3.
Check my math, but that would be 6KQ over 3R plus 2KQ over 3R, which gets you what?
8KQ over
8/3. Ah, but what does KQ over R equal?
150.
KQ over R equals 150. That's the significance of knowing what KQ over R equals. So, once you go through all the math, since you know what KQ over R is, then it's just a substitution process.
And then you know, you don't have to worry about fractions.
Yeah, 400.
Okay? And you could pick any point. You could have picked 1/3, you could have picked whatever, okay? Does that make, are we good? Okay. That was a good one. And again, I just worked it, I set it up by setting it, initially by setting it as 2R. If you had started off and made that R, you could, it would still work. But your fractions are gonna be introduced much earlier, and your fractions then are gonna be more ugly, because then down here, that would become R over 4, and then, you know, it would just get real ugly. Okay, now are we good? Let's go twice.
Number 15.
Which one?
Number 15 on the problems.
Where you're finding the difference in them?
Yeah.
Yeah, all you're doing is just use V equals KQ over R. And then just find the two different values of R and subtract them.
We only have like 30 minutes.
Because you got the voltages, isn't like 3,000, 2,000 or something like
Yeah,
that?
3,000, 2,000, and you have the charge.
Yeah, of like 25 nanocoulombs.
So then, yeah, you can just find those.
Yeah, if you really want to get fancy, you can factor out a KQ, because that's the same for both of them.
I was doing something weird, and I got it where it was like, the second one was 1.5 times the first radius, and then I want to figure out what to do.
Yeah, just find, just the easiest thing to do is just smash it out. Anything else going once, go twice? Sold. Sold my soul to the top of the
Oh yeah, Bert, just in advance, I got a little Asian zing on mine, so.
Got a little what?
Asian zing. It was the sauce we marinated our chickens in, so it's a little.
Teriyaki sauce then?
Just to let you know, Bert, I'll leave early next Wednesday.
You honestly think I'm gonna remember that?
I'm just telling you now, just to say that.
I just want to let you know that I'm sticking down and paint it on his desk. He'll remember that.
This is making me so mad.
This is like, I think,
I felt like I already eat it.
4 times 10 to
You're
You had help?
Oh, you said 28.
What?
20.8.
This assignment is going to put me in a bind. A bad bind.
Tonight's assignment, one bind.
Because it's closer to where the electric field is coming.
Hopefully, the next assignment